Today we will be discussing about photoelectric effect. In our previous lecture, we discussed about the wave particle duality, and today we will be taking up photoelectric effect. So basically, what was observed that when a blue light strikes a cesium target, it emits electrons. The electrons are emitted from the cesium. Whereas if a red light strikes the target, there is no emission as such. But this emission, whether it is a blue light or a red light, is in violation of the wave theory of light. So Einstein explained it that light is composed of photons as given by the particle nature concept. And to emit an electron from the cesium atom must absorb a single photon, and the energy of that single photon should exceed the ionization energy of the outermost electron. So if the energy of the incident photon is greater than the ionization energy, the electron will be emitted from the cesium atom. Where in the case of the blue or red light, the blue one is having a sufficient amount of energy, and that is sufficient to ionize or to emit the electron, while the red photon does not have it. You can see that when there is a light strikes a metal surface, electrons are emitted, which constitute the current, and you can have a reading in the ammeter. This shows that when a photon comes, electron is emitted. Here you can also see when there is a radiation on the metal, photoelectrons are emitted. So an experiment was designed. You can see a tube with a cathode and anode. When the light falls on this cathode, a monochromatic light falls on this cathode, this is a metallic cathode, photoelectrons are emitted, which are attracted to the anode, and a current flows in the circuit, which can be noted through this galvanometer. And if we plot a graph between the photocurrent and the applied voltage, we get this kind of a curve. So in the forward biasing, there is an increase in the photoelectric current, which becomes constant. And if we reverse the biasing and increase it, we will reach a point where the photocurrent will become zero. So this negative potential at which the photocurrent becomes zero is called the stopping potential. And the inferences drawn from this experiments were that the maximum kinetic energy is independent of the intensity of the incident light. In fact, it depends on the frequency only. Electrons are emitted almost instantaneously, even at very low intensities. No electrons are emitted if the incident light falls below the threshold frequency. And this threshold frequency is different for different metals. And the maximum kinetic energy of the photoelectron increase with increase in the frequency. So Einstein, after all these experiments, came up to a conclusion and postulated in 1905 that all electromagnetic radiation can be considered as a quanta, which is a bundle of photons, and each photon has an energy given as h nu, which is equal to hc by lambda, where h is the Planck's constant, whose numerical value is 6.6 × 10⁻34 Joule/second. And a photon of incident light gives all its energies to a single electron. Like if one photon is incident on the metal surface, one electron will be emitted corresponding to it. It's not so that two photons emit one electron or one photon emits two electrons. One will emit only one. So electrons injected out of the surface of the metal without any collision with other metal atoms before escaping, and the kinetic energy of the emitted electron is given as half MeV square, and Me is the rest mass of the electron. H nu is the energy of the incident photon. Phi is a work function, and this work function denotes the minimum energy or the threshold value of the energy that is spent in emitting the electron. This is the energy of the incident photon. Phi is the amount of energy spent in emitting it. So the energy of the emerging electron is the difference of the two. And phi is the threshold value. And this is where value of this work function phi is different for different metals. And the higher the work function, the more energetic the incident photon should be to emit the electron. So finally, I think came to a conclusion that the energy depends on the light frequency and the work function and is independent of the intensity of the incident light. And each photon may have enough energy to eject an electron immediately, and there are no photoelectrons ejected below a certain cutoff, regardless of the intensity of the incident light. And this cutoff frequency corresponds to the wave function. And as the frequency of the incident light increases, the kinetic energy will increase linearly once the photon energy exceeds the wave function. And this photon will carry a momentum, which is given by h by lambda. As we see that the photoelectric effect, the photon is incident and an electron is emitted. And the reverse is the electron is incident and a photon is emitted. So if a photon is emitted with a high energy, this process is termed as X-ray production and has a minimum condition that the energy of the photon, emitted photon, should be in the range of 100 electron volt to 100 kilo electron volt. You can see that the electrons are emitted from this cathode. They strike a metal target and the photons are emitted. So Röntgen in 1895 carried out his experiment with a tube that is called Röntgen tube. It is a simple cathode ray tube. Here is the cathode. Electrons are emitted and there is a metal target. It is tungsten generally. And when the electrons strike this target, photons are emitted. These are high energy X-ray beams. And the electrons are emitted due to the thermionic emission. The electrons are deaccelerated by this anode. And the breaking of this radiation is called Bremsstrahlung. Part of the kinetic energy of the incident electron is used in production of the X-ray, like the wave function there. The most energetic photon is given as, this is the energy of the emitted photon, which is Hc upon lambda minimum, where lambda minimum is at the threshold wavelength. When we plot a graph, we have like this. This notes that there's lambda value of lambda increases. There's an increase in the energy of the emitted photon. So the energy of the emitted photon depends on the wavelength. So we end our talk here today. Today we discussed about the photoelectric effect and the basic principle of the production of X-ray. The X-ray is in itself a new branch of study, and that requires many lectures for it. We will be discussing it in future whenever we get time. So today I ending it here. After this, we will be switching over to Compton effect. and after that, consequently, to quantum mechanics. So in our next talk, we will be discussing about Compton effect.